Okay, today we're going to talk about internal energy and getting work information from delta U. Why do we care about this? I'm going to share screen and show you why this is awesome. Share. Cool. Okay, so you should be seeing a piston moving back and forth following a pressure versus volume. In engineering, they call displacement curve. What do you think? It's interesting that P and V, or P and displacement, follow a particular functional, which means, sorry, a particular function. And that function is that inverse relationship of P and V. Now, depending on how we define our system, is this a completely isolated system? Is it an open system? Is it a closed system? Is it adiabatic? Is there no heat being transferred? There are so many different aspects of defining our system that we need to take into account to mathematically determine how much work energy we're getting out of this piston, also known as an engine. Cool. Okay, so what we're going to do is I'm going to talk about how we get information from how this thing, like what thermal energy is coming out, how we can convert that into work, which is always the goal. Okay, stop share. Cool. Okay, so now let's talk about delta U. So delta U, internal energy, it's a state function. And by state function, I mean that I can say this becomes du for infinitesimally small changes. Delta U, big changes, du, little changes. You will be asked to make assumptions in a lot of your homework problems that will get you to go from du to delta U and delta U back to du. And you have to recognize whether or not you can make those choices if the change in whatever parameter, so if it's delta star, can become d star if the changes in star are really, really small. All right. So this is equal to Q plus W, that's first law. Heat plus work. But we can't just say this is equal to dq plus dw because these are inexact differentials. They are not state functions. They depend on the path that's taken. So we represent that with these little hats on the d's that tells us we cannot say dq equals delta q. This means no. No. All right? But what we can say is that if I were to integrate du from some initial to some final state, that would give me u evaluated from the initial to the final, which would give me delta u, which again is u final minus u initial, which is what this notation represents. So that means delta u is equal to the integral of dq plus the integral of dw. And because these are inexact differentials, this becomes a line integral, which means you're integrating along the line and along the path. We're not going to do that. It's not that it can't be done, it can, but you have to know what that function is, and that's what we can't do. That's too hard. There's too many variables. If this is hot, and I'm losing heat energy, what's the function of the loss of heat energy? It depends, right? It depends on the material. It depends on how many pressure points this is. It's losing heat differently from the air or to the air versus to my hand versus to this handle. So many variables. It's trying to quantify things like friction. You can't do it, so you can only approximate. So that's when we say this is just then equal to Q plus W. So because again, inexact differentials, that leaves us with only being able to represent the change in heat as just Q, or the change in work as just W. So delta U equals Q plus W. We are going to confine our system to having no heat change. So for Q equals 0, we are imposing this. And if we impose it, that means delta U equals just work. Cool. We're going to focus on this with no heat change. So we're going to focus on this type of system, develop the relationship between delta U and work, and then when we get back to understanding and exploring this relationship, then we'll add Q back in. Okay? Okay, So now we're going to just focus on expansion work, and remember that Q is 0, so delta U equals Q plus W. And so because we're getting rid of Q, that means that this now actually becomes something we can quantify. And so here is the picture of the piston that I just showed you. There's a bunch of little gas particles inside, and then I've got a force pushing against this piston, and it's moving back and forth against an external pressure. So there's gas particles out here pushing this way, and there's gas particles in here pushing that way, and this force against this piston is what we're going to be relating to the work done by the system. Okay, so because the change in work is equal to force times a distance. And it's done by the system. So we're going to be losing. It's done by the system, which means the work is being expended. And so that means it's losing that energy. So it's minus change in work is equal to F. And I'm going to say that this small amount of change is a dz. So that's the force times that distance. Now, because I can make this quantity infinitesimally small changes, this dz, that means that this inexact differential of work can actually now become an exact differential because I can relate it to something that is infinitesimally small in its change, and that we can quantify. So if I then move the negative sign over, this becomes minus force dz, which is great. But if you want to recall, P is equal to force over area, which gives me then, which then says P times an area is equal to force. Well, that's cool. So if that's the case, then I can take P times an area and put it into here. So dW is equal to minus P times an area dz. But this, an area times a dz, well, that's just a change in volume. That's cool. Minus P dV. Hey! Awesome! That's cool. Okay, so we now have dW is equal to minus P dV. Yay! We're going to use this all the time. Okay, so the total work then is now, so expansion work is now dW is equal to minus P dV. Okay, but now there are some caveats. So do we have a constant external pressure, or does the external pressure change with respect to the pressure in here? So let's first start off with a constant external pressure. So P external equals constant. That means that dW is equal to minus P external dV. And so the external pressure has nothing to do with the change in volume here, which means that if I were to integrate this becomes the work is equal to minus P external integral of dV, because P external does not depend on the volume, which means the work is just minus P external times delta V. Sweet. So this is called free expansion that is irreversible. Now let's talk about the term irreversible. That means that as this piston is moving out against this P external, there's no possible way to get back out all of the energy that went into the work of pushing the piston away. Cool. We're going to talk about reversible and irreversible a lot. Another irreversible process, me taking this coffee mug and smashing it. It's not possible to then put it back into its original position or original state. So if you think about that, what would be the benefits of being able to put energy out from the system in terms of work and then to gain it back again? What would be the benefits of that? Good food for thought. Okay, so that's irreversible free expansion. Pause. Expansion work again. Okay, let's assume that this is expanding into a vacuum. I've been binge watching Star Trek a lot, and what really makes me mad is that they've got explosions in space, and I'm like, it's a vacuum out there. You're not going to have oxygen. Why is there an explosion? Go team. Anyway, but let's assume that this is against a vacuum. So if P external equals 0, or a vacuum, then what? You've got a force this way, but is there a force pushing back this way? No. So work is equal to minus P dV, but if P equals 0, well, that means the work is equal to 0. So there's a mathematical way to approach this. But think about what it means here. If you're pushing against a vacuum, are you pushing? Are you putting any work in? Or are you just like, the piston's moving that way because there's a vacuum? So there's no work associated with pushing against a vacuum. Cool. Okay. Now I want to talk about an expansion against a constant, or sorry, not a constant pressure, against a not constant pressure. So if we're going to expand against a pressure that itself is going to change in a way that we can monitor, then we might have access to retrieving some of that energy. We're getting to reversible work. Okay, so reversible work means that, let's assume, actually let's write this out. So work is equal to minus P dV, and so for P equals constant, we got work is equal to minus P external delta V, and for P equals 0, we have work equals 0. So if I were to do pressure versus volume, let's think what this looks like. Okay, and again, this came from equals the integral of minus P dV, which is equal to minus P delta V. Okay, an integral, you may recall from your calculus days, is the area under a curve. Well, if P external is here, and my delta V goes from state 1 to, or state initial to final, so we've got an expansion, then that means it's P, this value, times dV. Well, that's just, well, delta V times P. That's just the area under the curve, or the square. If, however, I want to say follow pressure volume, an ideal gas, so if this is an ideal gas, and it's expanding from this pressure, or sorry, from this volume to this volume, it's going to follow that isotherm, and I call it an isotherm because delta T is zero, the temperature is 0, so delta T is 0. So this is what the ideal gas law says. So P is equal to nRT over V. So for an ideal gas, this is the path that the pressure is going to follow. All right. If I want to get the area under the curve, which is the work, this is the shape of the amount of work that I can get if I know the function that my gas follows. If my gas is an ideal gas, I know it's going to follow this function dependence, which means the area under this curve is going to be the work. Well, let's explore that mathematically. So the work is equal to minus P dV, and I should put that. And what I want to do now is I want to integrate from this volume change, but I know that my pressure depends on the volume, okay? Which means, I'm just going to go ahead and say that this now becomes the work is equal to the negative integral of P as a function of V dV. So because P is a function of volume, I can't take it out of the integrand. This part is called the integrand, by the way. All right, but what is my function for P? It's right there. So I've got work is equal to minus integral nRT over V dV. Glorious. I know this value. I can integrate dV over V. nRT is a constant, which means I can take that out. So this is equal to minus nRT integral dV over V. And this is where, pause for everybody, we are going to do a lot of integration, and this is one of the reasons I encourage a lot of students to take my quantum class before we take my thermo class, because the thermo work is actually more challenging because you can do all of the math. The other math is more conceptual stuff, and I kind of just show you how to do it. Whereas this, you should be able to do these types of integration. So you really are capable of doing all the math in this class, which is so much fun. Okay, but how do we solve this integral? Well, hopefully you recognize work is equal to minus nRT log of the volume evaluated from the volume initial to the volume final. Hopefully you recognize that. If you don't, fear not, you are among friends. We will divert to Atkins, resource section. I have it marked. It says integrals, common integrals. Go team. So pause me and take the time to look this up. But if you look at integral number, can't even find it. A2. Go team. Pause, look it up. Every time you come across an integral, don't take the time to solve it. Integration by parts, iterative method, there's a bunch of them, which are all fantastic methods. And if you want to, I encourage you to do so. But use them as tools. Look them up in the integral table in Atkins, and then just plug it in. That's how you solve integrals in this class. Okay, so this means that we've got, I'm going to pause and erase and rewrite real quick. Actually, never mind. I need all of this to explain. Okay, so this then becomes minus nRT log VF minus log of VI, which then becomes, I'm going to write this up here, minus nRT log VF divided by VI. Cool? So when you are asked, well, what is the work for a reversible expansion? So P equals reversible, W equals minus nRT log VF over VI. Okay, so now we've got from work is equal to minus P dV. From this, we have irreversible, P is a constant. Vacuum, P is 0. Reversible, P is going to change with respect to the way that the gas in this piston changes. Okay, so what this means is P external follows P internal. You might think that's weird. It should be. Reversible processes are not really theoretically, well, they're theoretically possible. In reality, they are not possible. But look how the mathematics changes. Because pressure for a reversible process depends on the way that the internal pressure is changing, that means that your mathematics for the work is different. You've got nRT times log of VF over VI, whereas here you have minus P external, the value, times delta V, just the change in the volume. Different mathematics. This is why I encourage you never to memorize equations, because it depends on the system that you're dealing with. Okay, other thing, let's compare, let me find the purple marker, or black marker that works. Let's compare these two. If I were to say, okay, irreversible, oop, that doesn't even work, irreversible, overlay that with, oh my gosh, irreversible, overlay that so if this P external, or I could have it here, this P external, actually it would be down here. Eee. So this P external is going to be what the system ends up against, because once you have this piston pushing against this P external, if this P external is a constant, once it's met an equilibrium and P internal is equal to P external, it's no longer going to push, because you've got now equal forces on each side. So that's why this work that you get from an irreversible process will be less than the work you get from a reversible process. Go team. And if you think about what that means, the work from an irreversible process is less than the work you get from a reversible process. Where do you think the difference in the work energy goes? Lost to the system, or sorry, lost to the surroundings. So ideal cases, we can follow and go back again along this curve. Irreversible cases, you can only go back against the external pressure. All right, that does it for expansion work. Cool.